So now we are going to discuss gravitational redshift. Gravitational redshift. Gravitational redshift for of a light emitted from the surface of a star. And for simplicity, we are going to assume the star is spherical, so that the exterior solution is given by the Schwarzschild solution. Okay, so gravitational redshift from the surface of a star. So we are assuming that the star is spherically symmetric. So the exterior Schwarzschild solution is ds square is equal to 1 minus 2 gm by c square r, and we have chosen a unit in which the Newtonian gravitational constant capital G is equal to 1. We have taken G is equal to 1, and the speed of light is also taken to be 1. Okay. So, or in other words, we can write it like this: 2m by r, c square dt square is equal to dr square by 1 minus 2m by r minus r square d theta square minus r square sine square theta d phi square. This is equation number 1. Here, this m, if we take g is equal to 1, c is equal to 1, then this m is called, this m is the mass of the object, mass of the star. Or we can also define this m in our usual units. This m can also be defined as gm by c square, where now capital M is the mass of the star, g is the Newtonian gravitational constant, Newton's gravitational constant, c is the speed of light in vacuum. Okay, so this m is called the geometric mass. Geometric mass of the object. Okay, m is called the geometric mass of the object, and it has units of length, and has the unit of length, and has the unit of length. So if you take g equal to 1, c equal to 1, then m represents the mass of the object measured in geometric units. Okay, and you can also define m as g capital M by c square, where m is the mass of the star. This m is called the geometric mass of the object, and it has the unit of length. And what are the physical meanings, physical significance of these coordinates t, r, theta, and phi? The coordinates t, r, theta, phi are the coordinates as observed by a distant observer. Okay, meaning the meaning is this. Here, t is the time measured by a distant observer, which is very far away from the source, or far away from the star. And r, theta, and phi are the usual spherical coordinates. Okay. Now let us consider an atom on the surface of the star, and that atom is emitting some light. Okay, so for an atom on the surface of a star, and emitting light. Emitting light. For this atom, which is on the surface of the star, and let us assume that this atom is not moving. Okay, the atom is not moving, so that dr is equal to 0, d theta is equal to 0, and d phi is equal to 0. So for an atom which is not moving on the surface of the star, we have dr, d theta, d phi equal to 0. So this metric becomes so that the metric given by equation 1 reduces to the form ds square equal to, so dr is equal to 0, d theta is equal to 0, d phi is equal to 0. So these three terms won't be there, only the first term would be there. So yes, ds square is equal to 1 minus 2m by r c square dt square. So this we call it equation number 2. And then since the atom is on the surface of the star, so this r should be the radius of the star. So radius of the star, let us call it r0. Okay, so r0 being the radius of the star. Okay, fine. Next, the proper time interval. The proper time interval d tau as measured by an observer at rest in the vicinity of the atom. Is given by, okay, so what does it mean? It means that we have an observer which is at rest near the atom, and the proper time as measured by the observer is given by ds equal to c d tau. Okay, we call this equation number 3. That is fine. So if I use this equation number 3 in equation number 2, then I can replace ds by c square d tau square. Okay, so let us use it. So using equation 3, in equation 2, we get d tau is c square d tau square. We should get c square d tau square. This is equal to 1 minus twice m by r0 c square dt square. Okay. Now c square they cancel. Then if I take the square root of both sides, what should we get? This implies d tau, this will be equal to square root of 1 minus 2m by r0 dt. Okay, and this, if this quantity m by r0 is small, this m by r0, if this is a small quantity, then we can use the binomial expansion and retain only the first term. In that case, this becomes 1 minus half 2m by r0, 1 minus half 2m by r0, and half and 2 they will cancel out, and we shall get only m by r0. Okay, d tau. So this is binomial expansion of this and retaining term only up to first order in small quantity when m by r naught is small. In general, for the sun, say, for example, if we take the sun as an example, then m is approximately equal to 1.47 kilometers and r naught is equal to 6,96,340 kilometers. So this is approximately equal to less than 1 by 10 to the power minus 5. So this is a very small quantity for the star, which is the sun. So for a typical star, this is a very small quantity, and we are justified in using this binomial expansion. Okay. Hence, if dt equal to capital T is the time period of emitted light as observed by a distant observer and d tau equal to T0 is the period as observed by an observer at the source, that is at the surface of the star. Then this becomes T naught, this becomes capital T. So this is T naught, this becomes capital T. So we should have T naught is equal to 1 minus m by r naught capital T. Okay. As I said earlier, this dt is the time interval measured by an observer who is very far away from the source, and this d tau is the time interval measured by an observer near the source, that is near the atom, and this observer is at rest relative to the atom. Okay, so T naught is equal to 1 by m r naught, and this time period is inverse of the frequency. So this implies if I write it in terms of frequency, this becomes 1 by nu naught and 1 minus m by r naught 1 by nu. This is the frequency, corresponding frequency. Okay, where nu naught and nu are the frequencies corresponding to T naught and T respectively. T naught and T respectively. Okay. Next, what should we do? We multiply both sides by c, the speed of light in vacuum. So multiplying both sides by the speed of light c, we get c by nu naught is equal to 1 minus m by r naught c by nu. Now c by frequency, speed by frequency, what is that? That is the wavelength lambda. Okay, so this can be written as, so this expression, it can be written as, this implies lambda 0 is equal to 1 minus m by r0 lambda. Okay, this implies if I bring it towards the left, we have lambda equal to lambda naught, then divided by this 1 minus m by r naught to the power minus 1. Okay, So if I bring it towards the left, when we are dividing by this term. And since this again a small quantity, we can take the binomial expansion and retain only the first term. So this is lambda naught 1 minus plus m by r naught. Okay, so this implies this is lambda naught plus m times m by r naught lambda naught. So this means lambda minus lambda naught, this is equal to m by r naught times lambda naught. Okay, this implies delta lambda. Delta lambda is this lambda minus lambda naught. We represent it by delta lambda divided by this lambda naught. This is equal to m by r naught, where delta lambda is equal to lambda minus lambda naught is the redshift, is the change in wavelength. Is the change in wavelength as observed by a distant observer, by a distant, as observed by a distant observer. Okay, this is the wavelength as emitted by the source. This is the wavelength as observed by the distant observer. So lambda is larger than lambda naught because of redshift. For this observer, for this distant observer, this change in wavelength is this change in wavelength is a shift towards longer wavelength, is shift towards longer wavelength, longer wavelength. This change in wavelength is called the gravitational redshift. Gravitational redshift. Okay, so this change in wavelength is due to the influence of gravitational field on the emitted light, and this we call the gravitational redshift. As an example, in the case of light, originating on the surface of the sun, delta lambda by lambda naught, this is equal to m by r naught, and this is 1.47 kilometer divided by 697,000 kilometer, and this is equal to 2.12 into 10 to the power minus 6. This is a very small quantity, 2.12 into 10 to the power minus 6.